Zombie Apocalypse.
Okay, so today's topic, let's try to apply yung naging principle ng discussion natin last video lecture. But we will try muna sa isang compact steel section. So let's get ready to be neurorized. Suppose that we have this problem, a 9-meter simply supported beam carrying a uniformly distributed dead and live load of 7 kN per meter and 3.1 kN per meter respectively. So using a section of W18 by cross 50 or by 50 under ASTM standard A992 grade 50. So determine the flexural capacity and the demand capacity ratio under Flexure for ASD and Lrfd. So ano yung mga important parts ng problem natin? So given na 9 meter simply supported siya, dead and live load. So hindi pa kasama dito yung beam weight kasi hindi naman sinabi na inclusionaries of all dead load. And a section of W18 by 50, kukuha tayo niya sa AISC database shapes, no? Pinapresent ko na before. So also very important yung ASTM A992 grade 50. So I already have a separate video lecture about this one, discussing all possible ASTM standard and under steel section. So let's continue. No, how do we solve this one? Okay, for the solution using AISC database, no, ito yung mga makukuha natin. Na-discuss ko na rin dati kung paano kinuha individually yung mga values na yan. So because of this, no, dahil binigay naman at sinabi kumuha naman tayo sa property ng steel section, so we'll be adapting kung ano yung mga nandito na. So with the proper units, of course, and proper scientific notation. So we are talking about ASTM A992 grade 50. So na-discuss natin ng FY niyan is around 345 megapascal. So that's around 50 KSI. So to continue, no, na-discuss ko dati na yung H value na kino-compute natin is just only the T in this guys. So yung H natin, definition ulit niya, it is a distance free from the stiffeners or the fillets. So therefore, ang computation niyan, that would become H is equal to total height D minus twice of the K design. Okay? So diniscuss ko na paano natin na-arrive yung itong formulation. So as simple as the linear, since using algebra tayo, D minus 2 of the K. So yun lang yung makuha natin yung T. Or simply the H. So we will get H is equal to 407.6 mm. So saan ba tayo usually ngayon magsisimula pagka nag-analyze tayo ng mga gatong section? So we always start from the check for compactness. So tingnan natin sa table na na-present ni NSCP 2015, ano yung applicable? Okay, looking on this. So dahil plain lang yung binigay na W18 by 50, it's automatic na yung ating top flange is under unstiffened. Wala kasing inattach na particular plate or any structural steel section doon sa top flange niya, or maybe on the compression flange. So therefore, we can simply say that it is under unstiffened. Yung sa web naman, dahil meron ka naman nilagay na fillets, dahil may fillet siya, so it will fall under stiffened. Okay? Ngayon, so saan dito yung magka-qualify? So kung tingnan natin yung table, kung titignan nyo maigi yung 1 and 2, okay, nung nasa unang table, and also don't forget the 3. Okay, pwede yung 3. Kaso yung number 3 cannot be applied because of the statement here, ano? So there's a special property on statement number 3 of the unstiffened section that is not applicable to our given. So that leaves us to 1 or 2. Ngayon, saan yan yung pipiliin natin? Basahin muna natin, flexure in flanges of rolled I-shape section channels for 1, and for 2, flexure in flanges of doubly and singly symmetric I-shape built-up. Number 2 cannot apply since we're not dealing with built-up kasi predefined yung ating section. Kumbaga, siya yung pinaka-base section. So therefore, number 1 will apply. Now, for the stiffened section, for the titawag nating web condition, so you will start reading 9, 10, Okay, 11 and 12. Most likely 12 will not apply kasi hindi naman siya HSS or RSS. Number 11, this is singly symmetric, no? Which is our W section is said to be doubly symmetric. So that leaves us to 9 and 10 only. So which is, kung titingnan natin yung 9, flexuring webs of doubly symmetric I-shaped sections and channels, while yung 10, uniform compression in webs of doubly symmetric I-shaped sections. So which will apply? Number 9 will apply for this section since is specifically yung shape natin is a doubly symmetric shape and we do not know currently ano ba yung pinaka condition ng uniform compression in web. Ibig sabihin yan, meron kang in-apply na special forces dun sa web natin. Ibig sabihin, may mga connection siya doon sa ating other section details, like hindi naman in-specify na nagkaroon ng dugtong pang ibang beam doon sa web. So meaning number 10 cannot be applicable. So that leaves us to number 9. So therefore, by this to cut this short, kapag ang shape nyo is nanggaling sa W shape, it's 1 and number 9 will apply based on NCP. So yung number 1 will be the reference for flange, and number 9 will be the reference for the web. So therefore, in continuation, we already discussed before na yung B is equal to BF over 2 since ito yung B natin na dinefine ni code at ito yung breadth of the flange. So sinabi ng isa sa mga section, nakalahati lang. So we found out that 6.5862 yung value ng BF over 2 TF and 9.4093 for the lambda P. So di na natin kailangan i-check si lambda R kasi ito di ba yung lambda P at ito yung lambda R. Pag yung lambda P natin ay yung value natin is nag more than lambda P, you have to check now lambda R. So lagi natin kina-question sa una yan, no? Kung napapansin nyo, we always ask that. Same as with the second one. Okay, so on the first, sa flange checking, naging compact kasi nag-less than ka doon sa lambda P. Likewise, for H over TW or for the web check, so lambda P was 3.76 squared of E over Fy. So yung E natin, yung 200,000 megapascal, yung Fy natin, 345 megapascal due to the given ASTMA na 92, grade 50. So we found out again that the web is compact kasi 45.1885 is less than 90.5302. So meaning if the flange and web are both compact, then we can conclude that the section is compact. So pag both of them are compact, then you can simply say the section is compact. Then we will use the flowchart under compact sections. Next is to check for the unbraced length condition. Titingnan naman natin ngayon yung given. Now, if you recall kanina, ang beam length natin is 9 meters. So, the beam length is 9 meters. So, ibig sabihin yan, automatically, walang dinefine na drawing. So, siya na ang ating immediate brace length. Unbraced length, I mean. Ang L sub B is defined as the unbraced length. Yung distansya ng walang stiffener na additional support do sa ating system. So, therefore, ano kaya yung code na pwede natin gamitin out of that? Using the compact section condition. Okay, recall that there is an equation residing to this. So, kapag compact section, ito yung pag-compute ng ating L sub P. Okay, yung pinaka-minimum value ng ating brace length. At saka yung L sub R natin, medyo may konting kabaan. Ito yung for the maximum brace length. So, una, yung minimum brace length, okay? Unbraced length, sorry, it's not minimum brace length, minimum unbraced length, okay? Para magkaroon tayo ng parang boundary, okay? Minimum unbraced length, tapos ito na may maximum brace length, okay? Unbraced, sorry, it should be unbraced. Yan. So, by this, we can now compute the value kasi kompleto naman. So, except for C, no? Wala sa table yung C. Pero sinabi naman, for a doubly symmetric I-shape, so define na natin kung ano ibig sabihin ng doubly symmetric I-shape, which is all of the W sections are doubly symmetric, then C is equal to 1. So, therefore, nothing to worry na, no? Lahat ito makocompute na natin. So, plugging all the given values based on the data for a W18 by 50 database. So, yung makukuha natin L sub P at saka L sub R. So, therefore, those units are in terms of millimeters, okay? Gagamitin nyo lang yung mga values na to na nandito with their default units. We already discussed before. So, then, we found out that your unbraced length, is more than the maximum unbraced length. So, therefore, usually, ikukumpara yung tatlong yan. So, ito yung magpe-prevail. Tandaan natin na may tatlong condition yan. Yung LP na more than LB, yung LB na nasa pagitan ng dalawa, LR at saka LP, at yung brace length na nagmo-more than ng LR. Okay? Malaga na makompute yan kasi ito yung magdi-define sa atin paano ko kumpitin yung nominal moment capacity under flexural strength requirement. Now, check for flexure. So, ano kayang code behind this one? So, dahil nagkaroon tayo ng dalawang code, di ba sabi ng code natin before, we choose the minimum value of Mn based on two checks kapag compact section, yielding at saka lateral torsion buckling that we already discussed in the past video lecture. So, for yielding, 506.2.1, Mn equals your plastic moment, also Fyzx. So, therefore, by using the data on the given table, then we can have 572.7 kN meter. Siya na rin yung plastic moment. Ngayon, titingnan natin yung lateral torsion buckling at i-qualify natin kung sino mas maliit, yung lateral torsion buckling value o yung yielding na 572.7 kN meter to stand for the nominal moment capacity. So, we now proceed with the lateral torsion buckling code. Now, in lateral torsion buckling, so we will check some code out for this. Okay, according to the said code 506.2.2. So, dahil nagkaroon tayo ng LB that is more than L sub R, so dito ay kukuha. So, therefore, Mn equals FCR Sx less than equal to plastic moment. So, the way we compute FCR is ito. So, may participation ng CB, C sub B, or the coefficient of bending. So, CB represents coefficient of bending. Okay? So, kailangan natin computein muna before we check yung value ng F sub CR. Ngayon sa C sub B, pwede nyo computein to gamit yung factored at saka unfactored. No worries naman na magkaiba yung sagot, okay? Kasi same lang naman sila na magiging sagot ng C sub B kahit i-factor nyo siya or i-unfactor, okay? So, for this discussion, I'll try to factor all the loads first and then if I will compute C sub B. There will be no different answer kapag ginawa natin is unfactored state. So, allowable state, i-add mo lang lahat ng load and then compute for this. They will have the same answer since magka-cancel out din naman yung loads natin based on the moments as a ratio. So, using DTR for LB that is more than L sub R, so Mn is equal to F sub CR Sx less than equal to MP. So, we need to compute FCR. But before that, we need to compute the coefficient of bending. So, ngayon, may code provision. So, before we move on that, para makuha pala natin yung yung strength from Lrfd, so we just multiply nominal moment by 0.9. And for AST, divide natin nominal moment by 1.67 as showed here. Okay? So, yung PBM M sub n is actually for Lrfd as mentioned. And si Mn over omega B, so siya naman para sa ASD. Ang pinag-usapan natin dito is ASD new. Okay? And Lrfd new. Kasi may old yan yung NECP 2001 may Lrfd na rin yan, but hindi pa ganun ka-sophisticated yung design code niya. Ngayon, how do we compute that? So, we will use this one na dapat less than or equal to 3.0. Ngayon, yung value ng monosymmetric parameter R sub M, so we will use 1.0 for doubly symmetric members. Tapos, we will now compute for Mmax, MA, MBMC. Yung Mmax, you just draw the moment diagram and then trace the maximum moment. But don't forget that all of these values inside this CB computation are all taken as absolute. Ibig sabihin, kahit negative yung computing nyo, you just get the positive value out of that. So, take the absolute. So, MA, MBMC can be calculated as the first quarter or the 1/4. Okay? So, 1/4 of a brace length, okay? Tapos yung absolute moment at the center line, meaning dalawang 1/4 or LB over 2. And then the third quarter or LB times 3/4. So yan yung magiging guiding principle. Tandaan natin, na ang brace length natin kanina is the same this span of the beam kasi di naman dinefine kung nasan yung stiffener location. So therefore, this is 9 meters. Okay, let's continue. So therefore, we get first, no, yung dead weight ng structure. So 74 siya, no? Kilogram per meter. So converted into kilonewton per meter. That's why we got this. And then total dead load. So we add the 7 kilonewton per meter as indicated earlier, plus the beam weight. So we will get 7.72594. So the live load as specified is 3.1, and then you will get this following. So again, the principle of load combination, the larger value will prevail, which is the 14.2311 prevails. So therefore, we will use W sub U of 14.2311. Okay, in computing CB, it's better for you to draw the bending moment diagram. So identifying all the parts. So tingnan nyo, may tigda 9/4 na kinuha tayo dito. This will represent the quarter points of the brace length. At kung mapapasin nyo, dinawingan ko ng konting X dyan. So that will represent unbraced condition. So therefore, yung letter A is the first quarter. Actually, pwede kayo magbasa ng left to right or right to left. Walang problema kahit magkabaliktad yung MA at saka MC kasi pareha sila ng multiplier na 3. So therefore, ito yung kukunin natin. Moment sa A, moment sa B, and moment sa C. So, to compute that, it's up to you kung paano siya gagawin. It's up to you to use the moment diagram. Or, pwede natin gamitin dito yung moment equation na napag-aaralan sa mechanics of deformable bodies. So, this will be my main equation if I were to derive that here. Kasi ito, 64.0401 kilonewton as a reaction. So, dahil wala naman changes to the equation, to the load, na consistent naman sa W sub U, so this equation will represent the entire span. So, given the function of x, so at x is 9/4, that will represent m sub a, at x is 9/2 or 1/2 of the brace length, and 3/4 of the brace length. So, MA, MB, MC. Then you will get this. So, then of course, yung maximum moment observed on the given beam section. Of course, if this is simply supported na walang end moments, so therefore, Mmax will be your MB. Nagkataon. Kasi wala kang end moment o yung moment sa magkabilang dulo na umiikot. Ngayon, tandaan natin na this is singly direction yung curve niya, no? Kasi tandaan natin na 'di ba sa computation ng RM, if you recall kanina, so ginamit natin RM is equal to 1.0, applicable yan sa double symmetric at saka single curve. Pero kapag ang ating beam ay nagkaroon ng execution ng double curvature, so ibig sabihin yan, RM is not equal to 1.0. May computation tayo dyan that I will try to show you in the next video lecture. So, computing CB, you will get 1.1364, then compare it to 3.0. Kapag less than, then we will adopt CB of that particular computed value. So, what if your CB is more than 3.0? Then, adopt CB as 3.0. Kasi less than or equal yung kanyang sign convention. Okay, so computing the critical stress, F sub CR. So, gagamitin yung dito yung value ng J. No? Ito, yung J. X sub X. H sub O. Okay, yung C natin, 1.0 na yan. R sub TS or the effective radius of gyration. So, you will get this. 121.2929 megapascal. Automatic na megapascal unit yan. Based on the prescription of the NSCP na pag kinumpit mo siya as Newton millimeter, automatic base unit mo is megapascal unless there's some code na pag kinumpit mo, lumalabas sa kilonewton. I will discuss that as we progress in this section, lalo na sa connection details. So therefore, if we know F sub CR, then we can now compute the nominal moment under lateral torsional buckling. So you will get 177.0876, which is we converted into kilonewton meter. Kaya nagkaroon tayo ng presence ng 1/1000 squared. Okay, don't forget that this is a converter from Newton millimeter to kilonewton meter. Then, note that it is less than MP. So therefore, we adopt nominal moment of less than MP, that is 177.0876 kilonewton meter. So what if your MN here under lateral torsion buckling, no, nag-more than sa MP? So i-declare natin na under lateral torsion buckling, it is already plastic moment kasi again, the system of linear inequality says that it is less than or equal. So, in comparison, di ba may dalawang value tayo under yielding. Yan yung para plastic moment value niya. Oops, sobrahan ng I. Naging yieldung ang dating niya. Okay, yielding. At yung pangalawa, ito yung lateral torsion buckling or LTB. So, we choose the least based on the code. No, na-discuss na natin before. So, we choose the nominal moment as 177.0876. So, ito yung gagamitin natin to compute Lrfd and ASD value. Now, for Lrfd, then we know that MU capacity is just a 0.9 of the moment nominal. So, we will get 159.3788 kilonewton meter. So, this is the answer for the strength requirement or the flexural strength of the material under design condition. So, Lrfd yung sagot diyan. Ngayon, to compute for the demand capacity ratio. So, before we move on that, since nakita natin na yung MU capacity natin, nag-more than na MU maximum, na yung MU maximum natin based sa bending diagram is 144.096. So therefore, we can safely say that this W18/50 is safe for Lrfd design. Now, to compute demand capacity ratio under Flexure or the DCR sub F, so you just divide the MU max over the capacity. So therefore, getting 0.9041. So meaning, dito pa lang malalaman mo na kung safe or unsafe eh. If your demand capacity ratio is less than 1, o sabihin natin less than or equal to 1, that is already safe or simply say adequate. Pwedeng safe, pwedeng adequate. Okay? So pagka nag-more than ng 1.0 in theory, that is unsafe or inadequate. Bakit in theory? Kasi in practice, there is what you call permissibility condition na hindi lahat kasi talaga na nagmo-more than 1.0 is already unsafe. Tandaan natin na napakarami na nilagay na factor of safety sa loob. So therefore, the designer's choice na yan kung paano niya ditingnan kung yung 1.05 is acceptable or not. So para natin malalaman yan kapag chinek mo yung tinatawag nating deflection. So siya mismo magsasabi kung ano ang code compliance niyan, kung papasa o hindi. Usually, ito yung pinaka-ultimate na tine-check. Ngayon, in actual, or in also, there's also another way that the designer can predict if the shape is safe or unsafe. Pero may kinalaman na dito, separate discussion ko naman gagawin, yung seismic requirement. Na for seismic requirement, dapat more than less than sa 0.95. Okay? So, di ko muna i-detail out kung saan galing ko dyan. We will try to discuss that as we progress. So, therefore, pag nag-more than 0.95, sasabihin na pwede na unsafe yan. Pero, theoretical side muna tayo dahil wala mo na kinalaman si seismic condition. Then, ang basis natin for being safe or unsafe ay yung 1.0 o yung pag nag-more than ka or nag-less than ka sa capacity, yung value ng actual maximum moment. For ASD, you just divide by omega B, that is 1.67. Okay, so we will get 106.0405 kilonewton meter. So that will be our capacity under allowable. How about the maximum? Babalikan mo yung beam. So you will get again the load and then take the maximum moment of that beam. So dahil simply support ito, madali natin mako-compute naman yung maximum moment niyan. So, we take all the loads, 7 plus 0.72594. Ito yung sigma weight dead load. Tapos yung 3.1, siya yung live load. So, you'll get 10.822594. And then, dahil simply supported tayo, magte-take effect yung WT L squared over 8. Then, we'll get 109.6126. However, we found out na medyo mas malaki yata si maximum moment kay capacity. So, therefore, we can say that this is in an unsafe section. So, ibig sabihin sa AST, hindi siya safe. So, para malaman natin kung itong unsafe siya, again, computein natin yung demand capacity ratio under Flexure, the maximum moment over the capacity. So, we found out, no, 1.0337, nag-more than ka ng 1.0, is an automatic unsafe under this criterion. So, ganyan po tayo kumompute ng flexural capacity kapag ASC Lrfd pinag-usapan using the compact section code. So, there will be a separate video lecture. What if the section is hindi compact? Doon na tayo pupunta sa other flowcharts. So, for the meantime, we will stop for this discussion and decide for the concept. So, you have to check now my next video lecture about what if the section is hindi compact. So, I hope that you have learned something new today. Thanks for viewing. And again, as our tradition, you have been Neurorize and see you in our next video lecture.